Now, now the first part is, remember this is March 16. This is March 16, 4.2, question paper 4.2. So the first part of the question is that complete the diagram to show the energies of electrons in a carbon atom, a C+ ion and a C- ion. So a carbon atom is, what is it? It's 1s2 and 2s2 and 2p4, 6 electrons. So 2p4 means it's 2px, 2py, and 2pz, and the 2p subshell has 4 electrons, so that means 2, 1, and 1. So that is what a carbon atom looks like. So there's going to be a 2s, and that one will have 2 electrons, 1 arrow up, 1 down, and then above that there's going to be a 2p subshell, and that one will have 3 subshells. So 1 arrow up, 1 arrow up, 1 arrow up, and so anyways, carbon +1 would be kind of the same. I'm not going to go through that. It's just 1 electron missing. So the down arrow over here would be missing, and carbon -1 would have 1 extra electron. So if I draw carbon -1, the only difference would be in the 2p subshell over here. So instead of 4 electrons, it's going to have 5 electrons. So 5 in the 2p would mean 2 of them would be paired. And I'll just quickly do this one as well. So this would be 2p3 because 1 electron lost. So this should be, and the 2s is still there. As anyway, so that's the electronic configuration. This is one of the allotropes of carbon, which is 60. What is the hybridization of a carbon atom in C60? So if you look at a carbon atom, the carbon atom is bonded to 3. It's bonded to 3 atoms. Like if you have a close look at it, the carbon atom is bonded to just 3 atoms, each carbon atom. So when it's bonded to 3 atoms, what is the hybridization? Is it sp2, sp3, sp what?
sp2.
sp2.
Okay, so it's going to be sp2. So if carbon was bonded to 4 atoms, that's sp3. Anyways, it reacts with an excess of hydrogen to form a single product, C60H(x). Use your answer to once to suggest a suitable value for X. So he's saying this thing reacts with hydrogen. So use your answer to suggest a suitable value for X. So what each carbon atom, how many extra bonds can each carbon atom make?
1.
One more, right? So it was already making 3 bonds. The 4th electron was delocalized. So, I mean, the 4th electron can be used to make another bond with the hydrogen atom, right? So 1 more, so that would make it C60 and H60. Sorry, C60. And H would be 60 as well. Because at the moment, the carbon is not making, it's making 3 bonds. The 4th electron is not doing anything. So the 4th electron would also be involved in bonding. So that would be, each carbon atom would be making 1 extra bond with H. So C60, H60, that's the answer. Now coming back to this, he's saying methyl benzene can undergo different reactions to form the product shown. The first one over here, reaction number 1 is Cl in the carbon chain. So what is, how do you put a Cl in the carbon chain? That is free radical substitution, and the conditions, so substitution, and the conditions for that would be
sunlight and would be chlorine.
Okay, so it's going to be Cl2, and that would be the reagent, and the condition would be UV light. So make sure you know the difference between reagent and conditions, because sometimes they'll just ask for the conditions. So Cl2 is the reagent, UV light is the conditions. How do you put a Cl into the benzene ring? So how do you do that? That is electrophilic substitution.
Lewis acid, aluminum chloride.
Yes, you would need aluminum chloride, which is I mean, this is electrophilic substitution. You can use aluminum chloride or even FeCl3. I mean, this is for bromination. So, I mean, these are the conditions written. So FeCl3 or AlCl3. So the reagent is going to be again Cl2 plus FeCl3 would be used. And remember, the difference between a normal benzene and arenes have the same reaction, like nitration of benzene. So electrophilic substitution of arenes are 2,4,6 directing, which means the bromine or the Cl will either get attached to position number 2 or it's going to get attached to position number 4. It's only in phenols. Like if you do phenols, the reaction is a lot more vigorous. So you don't need a catalyst. No catalyst is required in that case. So anyways, coming back to this, name the mechanism, we did that. Draw the structure of the product obtained. If reaction 1 is carried out using an excess of Cl2, reaction number 1. So my guess is that the only thing that will happen is that all three would be Cls, right? If there's an excess of Cl2. Is that clear?
Yes, sir.
Okay, so that's about this. Let's move to the next organic question. Just a second. So this one. Now this is transition metal complexes. Where's organic? So this one. Now the question is, the previous one was about rate of reaction, so forget that. The question is about a C-step. Describe the chemical behavior of C is the first one. Describe the chemical behavior of this thing. What is this thing acting as? So he's specifically talking about this thing, CH3CHO. What do you think this is behaving as?
Electrified.
It's behaving as?
Electrified.
Okay, so it looks like
Proton donor. It's like a
it is donating an H+1, so it's not
proton donor.
it's acting as an acid. It's acting as an acid because it gave an H+1. It lost an H+1 from this position and gave it to OH ions, and the OH ions so it basically provided an OH in H+1 to OH ion. That's what it did. Ibra, is this clear?
Yes, sir.
So is electrified, I mean, the incorrect answer would be incorrect.
No, that would it's not very clear whether it's behaving as an electrophile or not, because see, it's not really attracted to the OH ion. They're not joined together. I mean, is the point clear?
Yes, sir.
You talk about electrophiles and nucleophiles and free radicals when there's a reaction happening. Like, I mean, this thing is getting attracted to this. If this was the scenario that you had a carbon positive and the OH-1 was coming in and getting attracted to it, and they were forming some sort of molecule, but this is not what's happening here. The OH-1 is not getting attracted to the molecule. The only thing that's happening is that an H from here was lost, and the other molecule ended up gaining an H. I mean, this one ended up gaining an H+1. So it's an acid-base reaction. So it's behaving as an acid or a proton donor. Name the mechanism occurring in step number 2. Now, this is where the reaction is happening. So this is where the electrophilic nucleophilic thing would work. So what do you think is happening here? How can you, and remember, this is guesswork because you have not studied this reaction. So I'm assuming that this CH2-1, it ended up and joined with this carbon atom. So this is what I feel is that this carbon is positively charged, this one over here. And the CH2-1 is getting attracted to that particular positive carbon atom, right? Which is why the CH2 is joining with this carbon atom. And as it approaches, the double bond electrons are getting repelled, which is why you don't see a double bond. Instead, the oxygen has all the electrons because the double bond got repelled. So the question, first question, remember what did he ask exactly? He's asking for the mechanism. Now, the first question is this an addition, substitution, or an elimination? What is it?
Addition.
Okay, so this one is an, so this one, okay, this one is an addition. Now, the next one is it electrophilic or nucleophilic? Who's acting as what is this acting as?
Nucleophile.
So this is a nucleophilic
Addition.
But I'm pretty sure you can call it an electrophilic addition as well, because this other molecule is behaving as an electrophile.
Exactly.
So always remember that whenever you have a nucleophile always reacts with an electrophile. But
Sir, we haven't really studied nucleophilic addition, तो कभी नहीं पढ़ा. I mean, electrophilic addition पढ़ा.
no, we did study nucleophilic addition. Even if you hadn't, okay, this mechanism is not about if you had studied or not. But if you've read nucleophilic addition in that thing, aldehyde and ketones, where you learned about nucleophilic addition in AS in carbonyl compounds, where you had a reaction with CN-1, and the CN-1 would get attracted to the carbon positive, and the electrons over here would leave. Okay, you have studied nucleophilic addition. But that knowledge was irrelevant. You don't need to know that to answer this question. Is that clear?
Yes, sir.
I said,
Yes, sir.
and the reason why you call it a nucleophilic addition is that you always talk about the reaction from the perspective of the reactant. I mean, this was your reactant. The aldehyde, the ethanol molecule was your reactant, right? So there's a nucleophile that's attacking the aldehyde. So you always talk about, from the perspective of the reactant. Like if you go back, you would notice that the reactant is basically the aldehyde. That is your reactant. So you're going to name the mechanism from the perspective of your original reactant. Is that clear as well?
Yes.
So nucleophilic addition would make a lot more sense rather than electrophilic addition, because you're not talking from the perspective of this thing. This is an intermediate that was formed in the previous step. So you always talk from the perspective of the main reactant, main thing that is undergoing the reaction. As anyway, so that's
electrophilic addition कहते हैं.
No, nucleophilic now. Okay, this is the molecule. Okay, we don't care what that molecule is. Who's attacking that molecule? It's a nucleophile that's attacking it, right? So it's a nucleophile that's getting added to it. Is that clear?
जी.
So this one is nucleophilic. Philic addition. Anyways, the next one is the diagram below to show the mechanism for showing the relevant curly arrow. So that was easy. It's we drew it over there as well. So that's pretty much it. This is I think what we drew over here as well, that the CS2- was attacking the carbon positive and the double bond electrons were getting repelled. So now the next one is this is again transition metals. Just a second. So this one, this is again something else. Where's organic? So let's go over this. State and explain the relative acidities of ethanol and phenol. So I'll just refer to the notes. So relative acidities of ethanol and phenol. So where's that thing where we compared hydrolysis, then we did comparison of acids, right? So we discussed that alcohols are like really terrible acids, and he's comparing it with phenols. Phenols are relatively relatively good acids. And there's a table as well that you have to, somewhere down there, there must be a table that the alcohols are really bad acids. They only react with Na. Phenols are slightly better because they react with Na and NaOH. Carboxylic acids are like complete acids. So what's the reason behind that? The reason behind that is, okay, let me just discuss the reason over there. That when you have an ethanol molecule, CH3, CH2, OH, right? And it ionizes. What happens is that the alkyl chain has an electron donating effect, which is why the negative charge density over here increases. And if it increases, it attracts the H+1 back again and it doesn't ionize. So which is why the ionization is a lot lesser, because the negative charge density on the ethoxide ion is very high. So you're going to state that alkyl chains, so alkyl chain in CH3, CH2O -1 ion has an electron releasing or electron donating effect, inductive effect, electron donating effect. That's about it. And what this does is that the CH3, CH2O -1 ion becomes unstable. And the OH bond strength increases. Because obviously the O -1 would now attract the H+1 a lot more strongly, because the negative charge over here is going to be higher. And what happens in phenols? In phenols, what happens is that if you have a phenol and there is an OH and it dissociates, ionizes, the electrons on the oxygen, they overlap with benzene's pi electron cloud. So the ion becomes stable. So you're going to write the same thing, except for the fact that the lone pairs, they overlap with benzene's pi electron cloud. So this is the statement: lone pairs on oxygen. I mean, you don't even have to write this statement. Just write that it because it's a 2-mark question. You don't have to go into a lot more detail. So lone pairs on oxygen overlap with benzene's pi electron cloud. And this ion, which is C6H5O -1 ion, becomes stable. That's about it. It's just a 2-mark question, so you just have to write 1 mark for. So you don't have to describe all the things that the negative charge density would decrease and the H+1 would not be attracted as strongly. Is that clear?
So the phenols are more acidic than ethanols, right?
Huh. So phenols, where's the chart again? So remember, phenols are better acids compared to alcohols, and carboxylic acids are even better acids. Okay? So you have to know the reasoning. Why were carboxylic acids such good acids? Because in carboxylic acid, they also have a negative charge on the oxygen, but they have a very electronegative oxygen next door. So the electrons get completely withdrawn towards that oxygen. So the negative charge density is even lesser. So which is why they're even stronger acids. They ionize even more. So now the next one is you've got a phenol, and it's reacting with the phenols. This is electrophilic substitution. Now remember, electrophilic substitution happens vigorously with phenols and with phenylamines as well. So just before this, so no catalyst is required, and there's a reason for that, because in phenols and in phenylamine as well, The electron cloud, the lone pairs on oxygen, they overlap with benzene's pi electron cloud. So the charge density is pretty high, which is why the electrophiles get more strongly attracted to it. The same is the scenario with NH2, that in NH2, the lone pair on N overlaps with benzene's pi electron cloud, so the charge density is pretty high. So it's an activated benzene. The reactions are really fast. You don't need a catalyst. Polarization would happen on its own. And the bromine will get attached to positions 2, 4, and
Hello, sir.
6.
Sorry.
Yes.
I kind of vague on why the concentration of the electrons, they are all concentrated on 2, 4, and 6. I know it's, I mean, theoretically I know, but practically that's, I mean, I can't remember. I remember vaguely now. Do you mind if you can just repeat a little bit, please?
I will, but let me just be clear. You're saying why it's more concentrated on these positions.
Yes, yes, sir.
It's because, see, there's a lone pair on oxygen, right? And there's a benzene pi electron cloud. So the lone pairs and the electron cloud, they mix up over here because so what happens is that the negative charge on these carbon atoms, it becomes even bigger. I mean, if I do it with an actual benzene, like if there's an actual benzene somewhere. So this is what's going on. Like if I have, instead of the Br, if I have let's say an OH over here, right? So what happens is that O has these lone pairs, the two of them, and these lone pairs, they kind of start overlapping with the benzene pi electron cloud, and the negative charge density would then become much higher on this side, right? Because the lone pairs are also mixing up, so there's a lot of electrons over here. Is that clear?
Okay, I get it.
So position number 2 is relative to this, where this oxygen is attached. This is position number 2. And all the other electrons, they get repelled to the other carbon atom. So this carbon over here, the electron density is higher at this end as well. Because of so one side is negative, so all the other electrons, the remaining electrons, they kind of get repelled to the other carbon atom. Is that clear?
Yes, sir. Thank you.
Okay, so benzene has a pretty vigorous reaction. So when you add, where did phenols go? Just a second. This over here. So phenols, their bromination would be very vigorous, and their nitration reaction would also be vigorous. They don't need a catalyst for nitration as well. So you can do it with dilute nitric acid. 1 NO2 will get attached either to position number 2 or position number 4. Or you can also react it with concentrated HNO3, and the NO2 will get attached to all of the 3 positions. So if we go back, the question is dilute nitric acid. So there would be 2 products that should be formed. Either, so this is your phenol, and here's another phenol. So either the NO2 gets attached to this position, or it gets attached to position number 4, right? Then you have Br2, the conditions are aqueous, you don't need a catalyst. So just aqueous conditions should do the job, and an RTP. So in this case, you have an OH, and the Br will get attached to all 3 positions. If we had used concentrated nitric acid, then NO2 would also get attached to all 3 positions.
So don't we इसमें वो नहीं देखते कि NO2
नहीं समझ नहीं क्या कह रहे हो? Hello, Ibrahim, I can't hear you. So this one is electrophilic substitution, obviously benzene. And then he says phenylamine reacts with aqueous bromine compound to give compound F. Describe the appearance of compound F. Now, the appearance of compound F is a white precipitate. So this is
NO2 का हम ये 2,4 diagonal group नहीं देखते क्या नहीं? I mean, it attaches to all of them.
नहीं, ये दो, they're two separate conditions. Dilute nitric acid in the cold, ठीक है, would give you just one NO2. Most likely would give you one NO2. Concentrated nitric acid would give you 3 NO2s. Is that clear?
जी, लेकिन इसमें ये नहीं था कि one of the, I mean, there were certain groups जहाँ पे they would only attack वो 2,4 part of it, and फिर कुछ थे which would attack all of them.
हाँ, वो था कि there was basically two groups. We talked about just these two things. Arenes, ठीक है? In arenes, the benzene is not that activated because the carbon chain have electron donating effect, except they don't have actual electrons to donate. Okay, so the electron donating effect is very, very slight. So in that case, usually it's just one bromine or one NO2 getting attached. And in that reaction, you need a catalyst because the reaction, the benzene doesn't have a very high charge density. Is that clear?
Yes.
But the other one is phenols and phenylamine. They're the ones where the benzene is highly activated and it very strongly attracts the electrophile. So you have to.
इस बोर्ड का लिंक आप शेयर कर सकते हैं ग्रुप में?
मैं कर देता हूं, एक सेकंड. इस पे कर रहा हूं चैट में, ठीक है? Just did share the link. अच्छा, so coming back to the question now is, remember I've written phenol or NH2. I mean, both of the reactions are kind of the same. And in both cases, you're either going to get 2,4,6 tribromophenol, or if it's NH2 instead of OH, it's a phenylamine. So phenylamines will also have the same reaction, and they'll also give a white precipitate. So this thing over here is basically a white precipitate. He's saying that it's a phenylamine. Phenylamine is this thing. It's a benzene with an amine. And if you react it with bromine, then bromines will get attached to all positions, 2, 4, and 6, all of them. And phenylamine reacts with nitrous acid to form a diazonium salt. State the conditions for this reaction. So this one is about diazonium salts, the dye stuff that we studied. So that was studied where, one second. Phenols, they are probably dye stuff.
Yeah.
So this is nitrogen compound, organic nitrogen compounds. One second. Azodyes. So dye stuff, you can make azodyes. For azodyes, you need a phenylamine. And the first thing is you convert it into a diazonium ion or a diazonium salt. So this NH2 gets converted into N triple bond N+1, which is a very unstable ion. So the conditions required for that are NNO2 plus HCl, and the temperature's got to be less than 10 degrees centigrade. And what you do, now this is a very important reaction because you make very stable dyes out of it. Dyes need to be extremely stable. So you have this diazonium ion which acts as an electrophile. What it does is it goes and attacks, because it's a positively charged ion, it goes and attaches to or gets attracted to a highly activated benzene. So it's either got to be a phenol or it's got to be an amine. So it attracts an activated benzene, phenol or phenylamine, and it attaches and ends up forming an azo group with it, and that's your azo dye. It can have other groups attached to it, but that's the basic structure of what an azo dye looks like. So he's saying phenylamine reacts with nitrous acid to form a salt. State the conditions. So the conditions are the temperature's got to be less than
10 degrees.
10 degrees centigrade. And he's talking about nitrous acid. The thing is, NaNO2 and HCl, they basically end up forming nitrous acid, which is HNO2. So you can either write NaNO2 plus HCl, or you can also write nitrous acid, HNO2. But HNO2 is formed during the reaction when NaNO2 and HCl they react together. But the condition is temperature's got to be less than 10. Now the diazonium salt in 2 reacts with the alkaline solution of phenol to produce a colored compound G. Draw the structure of G. So I think he was talking about a phenylamine. And that phenylamine was reacted with HNO2 and the temperature was less than 10. And it would then turn into a diazonium ion. Now, the other thing is that it would then react with an alkaline solution of a phenol. So the phenol is an activated benzene with high electron densities at positions number 2, 4, and 6. So the N triple bond N+1 will be attracted to it, and the two would end up, so the two would end up joining together. And that's the final product that they were looking for. Is that clear? Yes or no? Is this clear?
Yes, sir.
So, and remember, azodized Walaju, this reaction, this specific reaction, this is very important. It comes in every paper, almost every paper. They always talk about this. It's a simple reaction. You just convert a phenylamine into diazonium, and then that diazonium attacks or gets attracted to an activated benzene, and they end up forming the azo group. So it's a very popular reaction that happens, comes very often in A2 exams. Now the next one is, you've got this compound, and compound H is a primary amine which has 3 peaks in its carbon-13 NMR spectrum. So he's talking about carbon-13. So let's ignore that for a second. So give the full name of the circled functional group labeled PQNR. So this one is an amide. Okay, so it's an amide with a D. This one is obviously a ketone. And he's referring to the full name. So what is this one?
C from CNC. This is secondary alcohol.
So it's
secondary.
That one is a
secondary alcohol.
Okay, so that's the secondary alcohol. Bhaskar, second, I'll count to you. Actually, Bhaskar, it's I'll just explain this very quickly. Remember, under extremely low temperatures, the NH2, you don't need to know the mechanism, Bhaskar. So all you have to know is that a reaction happens with NNO2 and HCl, or you can also call it HNO2, and a very unstable ion is produced. So this thing is extremely, extremely unstable. The reason it's got a positive charge is because it's lost its lone pairs during the reaction. So it's N triple bond N+1. So you don't have to be very specific, like you don't have to go into the details about this. You just have to remember that there's a diazonium ion, this thing is formed, but it's highly unstable. It's so unstable that if you raise the temperature above 10, it will quickly react with water. It will attract lone pairs from water, react with it, and it will decompose and form a phenol, and also at the same time produce NH4+1 ions as well. Okay, Bhaskar, is this clear? So no need to go into the details of how the electrons are being shared over here.
So is there any condition where it produces ammonia instead of ammonium ion?
It can if you just make it alkaline. If the solution is alkaline, then obviously it will form NH3. Okay, let me just and there was, I do remember one question on this as well, because if you make the conditions acidic, then obviously it's going to be NH4+1. But this one is an acid, so let me just quickly Google something. ChemGuide diazonium. Just hold on a second. So that's some reactions of diazonium ions. Yep. That's a, so you got N triple bond N+1 and NH4. Let me correct this one. Yeah, this one I wrote incorrectly. It wasn't making, it's making nitrogen gas. This is not, just a second. Let me correct this. It's not making NH4+1 to begin with. When it decomposes, although that's not really important, you don't have to remember the whole reaction. It produces nitrogen gas. You can make a correction over there. Is that clear? तो वो मोनी वाली बात ही नहीं वो both of them I wrote that incorrectly. Is this clear?
Yes, sir.
Yes, sir.
Achha. But again, you don't need to know the whole equation. That's not important. Now, coming back to this, that's a secondary alcohol. And now on the diagram of this thing below, draw a circle around any chiral carbon atoms. You have to look for chiral carbon atoms. So skeletal formula, this one has 2 H's, this one has 2 H's. Benzene can never be chiral. Remember, benzene is sp2 hybridized. So with 1 electron, not bonding. So that can never be chiral. This one is making a double bond. This one over here. This one is 2 H's. Is this carbon atom chiral or not?
Yes, sir. Chiral.
So this one is chiral. This one over here is 2 H's. This one has, but it's not chiral because it's got 2 CH3s on both sides. So 4 different groups. For chirality to happen, you need a carbon atom that's bonded to 4 different groups. Only then can it have 2 non-superimposable mirror images. So there's only one chiral, that's it. This one. Is that clear?
Yes, sir.
And then he says, draw a line through the bond broken by heating with dilute hydrochloric acid. Draw the structure of the smaller molecule produced by this reaction. So he's heating it with an acid. With acids, what you get is hydrolysis. So your amide links and your ester links, they break. So where did we do? Just a second. Did we do amides over here? Yep, I think. So anyways, this is formation of esters, formation of, I'll just quickly tell you, can't really find it. So whenever you have an amide, which is C double bond O and NH, okay, so whenever you have this thing, and you heat it with an acid or with an alkaline, there's acidic hydrolysis, there's alkaline hydrolysis. So this thing will break. This thing will turn back into a carboxylic acid. And this other thing will turn back into an amine. And the same is true for esters. Whenever you have an ester, you heat it with dilute acids. The ester will break. It will form carboxylic acid. And this one will form an alcohol. So remember acidic and alkaline hydrolysis. In alkaline hydrolysis, always remember that you'll not get the carboxylic acid. You'll get a salt of the carboxylic acid if he had used NaOH. The NaOH would end up reacting with this thing. So anyways, you've got an amide group over here. And so this thing will break. And he's asking you to draw the smaller molecule. And I think that's the only amide link. There is no ester link anywhere. So it's not going to break at any other point. This is the point where it's going to break. So that's CH3. Then you have CH2. I mean, you had CH2, then a CH2, then C double bond O. So there's another CH2. And then you've got a C double bond O. And that C double bond O will turn into a will turn into a carboxylic acid. So that's butanoic acid, I think. That's the molecule. That's the smaller molecule that's produced by this reaction. And you had to draw this.
Heating with dilute HCl will produce acid.
Huh?
Amide linkage break होके acid बनेगा.
Huh, one of them is a carboxylic acid, the other one is an amine. But obviously, in acidic and alkaline hydrolysis, the difference is that if you have an acidic hydrolysis, so you're going to get a carboxylic acid, but you're not going to get an amine. Instead, the lone pair on N will accept an H+1. So you will probably get R and NH3+1. Is that clear? And if the hydrolysis is alkaline, like you're using NaOH instead, so you're not going to get the carboxylic acid. Instead, you're going to get a salt of the carboxylic acid, like C double bond O, because the alkali will react with it. Is that clear?
Yes, sir.
Okay, so suggest what would be observed when this thing reacts with the following reagents. Alkaline iodine solution. So first thing, what's an alkaline iodine solution? It's a iodoform test, which is the iodoform test in AS was a test for specifically this structure. If it has this structure, there were two structures. Or if it has this structure, which is, I mean, this could be R. The other one was, it's a test for an OH, for an alcohol. And in both cases, the CH3 would break away. In both cases, the CH3 part would break away and it would form a yellow precipitate. So the CH3 in both cases would break away and it would form a yellow precipitate of CHI3. Now they're just looking for the observation, so you don't have to write any reactions over here. So does it have CH3 with a C double bond O? It does. It does have this. So if you do it with alkaline aqueous iodine, the CH3 will break away and it will form CHI3. And that's going to be a yellow precipitate. So that's the observation. So you just have to write the observation. The other part turns into a carboxylic acid. So that's the iodoform test. Remember the iodoform test. Universal indicator, that's if you know the colors, I think it's extremely acidic is red. Slightly acidic is orange. Green in the middle, neutral. Then blue, that's slightly alkaline. Purple, very strongly alkaline. So the question is, what is this compound? Is it an acid or is it a base?
The base.
And why is it a base? Well, what's the basic part?
The accepting of the electrons.
So the basic part is, remember the basic part, where did we do bases? This one. So the nitrogen bases, you basically have nitrogen bases, nitrogen have lone pairs. Except for amides. Amides are not basic because there was reason for that. That the lone pairs, they get completely attracted by this oxen next door, and they're not available to attract H+1. The lone pairs are the ones that accept H+1 ions, right? The lone pairs are the ones that attract H+1. So they're not basic. The others are basic. So you've got an amide over here. This amide is not basic. That's not basic, but you've got an amine over here, which only has, this is basic. So the H+1 would be attracted to that thing. So it's probably going to be blue in color because it's going to be slightly basic, just like ammonia. It's actually even a stronger base than ammonia. Amines, alkyl amines that have carbon chains next door. Why are they strongly basic? Because there's a carbon chain that has an electron donating effect. So the lone pair charge density would be higher over here, which is why they're going to accept H+1 more strongly. Okay? So that one would be slightly basic, not that strongly basic, just slightly basic, which is why This one is going to be blue in color. And then you have 2,4-DNPH. 2,4-DNPH is a test for identifying carbonyl compounds, just aldehyde and ketones. So I think this one is a ketone. So this is not a ketone. Remember, this is an amide. This is a ketone. So it is a ketone, so it's going to give an orange precipitate, 2,4-DNPH. And Tollens reagent was specifically used to oxidize aldehydes. But I don't think this molecule is an aldehyde. So I mean, this molecule over here has no aldehyde group. It's got a ketone group, but no aldehyde group. For aldehyde, the double bond O must be somewhere at the end of the chain. So let's continue tomorrow. Make sure I've sent you the notes, the links to the notes. Make sure you go through them. TK, we'll just practice more organic questions for now. TK.
Chal, theek hai, sir. Okay,
Thank you, sir.
thank you.
Okay, take care, everyone.